Hello. Can you guys all hear me? Everything good here? How you guys doing? Happy to be here? You've probably heard that a couple times today. So my name is Wes McDonald. I am the technical director at Turtle Rock Studios. And today I'm going to tell you about Evolve and what it took for us to ship our game on EC2. As it's the title of this talk is Hunting Monsters in a Low-Latency Multiplayer Game on Amazon EC2. There are a couple different points that I want to cover. First, I'm going to tell you about what is Evolve, and then we'll talk about what it takes to run a real-time game in Amazon. And then a large part of our system is a REST-based server reservation. This allows us to allocate servers for players to use. And then I'll talk about how we automated everything, because that was a huge key for our success. After that, I'll talk about how we took the whole system global, and then our auto-scaling system. And then I'll give you a good idea of kind of how we take a good view into our monitoring and metrics so we can keep an eye on this big system. So the first thing we'll talk about is what is Evolve. And before I try and describe it in words, I think it's better if I just show you a video here. See if this starts. Is it not playing audio?
Big. Monster tracks, broken trees, animal corpses, and bird sign are all indicators of the monster's presence. The round ends when one team is eliminated, or the monster makes it to stage 3 and destroys the power relay.
All right, so then I guess I will be describing it in words. So Evolve is a 5-player action game. The key point is that it's 4v1. That's 4 first-person shooter hunters versus a third-person shooter monster. And they're all in the same game, playing against each other. The hunters are trying to kill the monster, so they're chasing him around the map. And then that monster is trying to eat wildlife. And when he eats more of the wildlife, he can get stronger, stage up, and then he can turn the battle back on the hunters and go and kill them. So a big point is that it is 5 players, but beyond that, there's also 30-plus AI wildlife that the monster's going after. And so that gives us a very high equivalent kind of player count that you would see in a normal first-person shooter. That would be, let's say, 40 players or something like that. We have a very similar kind of CPU processing load. We are using the Cry engine. And what that brings is it handles a lot of the rendering and the physics, and we build kind of our game logic on top of that. And it's kind of the package that everything's wrapped in. And that's what the base of our system is built off of. And so using the Cry engine and putting this all together, we have this process that builds everything together. And it's the executables. We package up these assets, and those assets are kind of the textures or the animations, a lot of the models, the maps. Everything gets packaged together. And then we create 2 different packages. One is the client, and that we ship for Windows PC, Xbox One, PS4. And then we also have the server version, which we ship for Linux. And it's stripped down. We take the textures out, like we don't need those on a server. And anything else that we don't need on the server, we kind of take out of there to reduce the space. And so what you end up with here is a client that can connect to a dedicated server binary given a proper IP address and port configuration. So they would have to know where on the internet to go, what port to talk to. But just through this process, we have that together. And so given that, we can start talking about what it takes to bring that into AWS. And so that's running a real-time game simulation in Amazon. So traditionally, games have been co-located. When you want to run an online game, it's pretty common to go and rent space in a data center, start physically putting hardware in there. You have to have teams of people all over the world ready to maintain that hardware. And you have to know or kind of guess what your load is going to be at launch. And that's a really difficult thing to do. And it's not the easiest problem to solve. And there's actually some interesting solutions to that, and you can go down that path. But one really good solution I've found is that to use the cloud. And using the cloud simplifies a lot of that maintenance and requirement for hardware and allows us to more easily just build it out in a virtual infrastructure. I think all of you guys are pretty aware of what the cloud is, being here at AWS reInvent. So one of the most important things I noticed, though, is that when you co-locate or you're running your own infrastructure, you might have to maintain your own switches and hardware. And so you would kind of estimate what your traffic loads are going to be, and you'll purchase routers that maintain that and can handle those kinds of traffic loads. And when there's a problem, it affects 100% of your application. Whereas if there's a problem in Amazon, you might be one of 1,000, 100,000 people. And so a small problem in Amazon only affects a small problem, or a small portion of people that in that service, whereas if it's your own infrastructure, any problem can be a major problem. So one of the biggest barriers that we ran into trying to work with the cloud is getting everybody comfortable with the fact that we were going to run a real-time simulation in a virtualized environment. And a lot of people had some doubts that that was even possible. There was a lot of talk about CPU time slicing, noisy neighbors, like if someone's eating CPU next to you on another machine or on the same machine, they could just be taking your resources away. That was a lot of the fears. So we went through a lot of process making sure that all of the resource allocation is completely strict. When Amazon says you get a certain number of cores or compute units, you actually get that, and that is yours. No one can take that from you. When you get a certain amount of memory, you actually get that. That's yours. Same with network I/O. And so using our automated testing, we were able to prove that it does work. And also, I can add confidence for you guys if you're talking about doing this, that we did ship it. It was successful. And so you can use that as well if you like. So when moving something, when trying to determine what kind of hardware you need to kind of understand what your resource requirements are. And for us, we knew that we wanted to be memory bound and not CPU bound. And this is really important because we were a lot more stable, kind of measuring exactly how much memory we need. We knew that as long as we stayed within that, it was really stable, that we can always kind of shut the processes down, load them back up, and we'll stay within our memory range. Whereas CPU, if you're constantly running at 90% CPU and some other process on the OS decides to like back up logs or something, you could see a spike in CPU that would drop every process on your machine, whereas memory was very stable. So when we were trying to determine what AWS instance would work well for us, we used automated testing. And we have a mode in our game that allows us to play 4 bot humans, or the hunters, versus 1 bot monster, and they can just play over and over and over again. So we just took every instance we could find in Amazon and just ran as many machines on them as we could until they just burned to the ground. And then we kind of figured out where the best balance was. And for us, that balance turned out to be the C3 instance. It gave us the best CPU to memory ratio. And then it also came with the ephemeral drives, which we actually took a lot of advantage of those ephemeral drives. We RAID 0 striped them, and then that gave us a ton of I/O ops, essentially for free on the machine. And one of the core concepts of what our game does is when players start a game, the actual dedicated server process will launch from a cold start and have to load the whole level up. So having all that I/O, bursting I/O, was really, really good for us. Also, it gave us a lot of space for the executables, the assets, all of our logs. We also have core dumps. The game does crash sometimes, I'll admit it. And so we want to keep those around so that we can investigate that and understand why it happens. And then beyond that, we also use the ephemerals for our swap space. Even though we set and we know exactly how much physical RAM we're getting in our VMs, we made sure that we had a little bit extra in our swap space for if we want to go onto a machine and debug something, or during a core dump process, or just for whatever reason. We don't want the whole thing to just burn if we go a little bit over that memory. So then beyond that, we've also got network we had to worry about. And so with the C3, it did have the enhanced networking. That was not a huge gain for us. We actually found that all of the latency to all of the instances in Amazon were actually really good. It's actually the internet that's your biggest latency worry. And then beyond that, we have a really low bandwidth UDP protocol that we're using, and a lot of that comes from the fact that we're using peer-to-peer as well. We have a fallback path to a peer-to-peer based game, and so we optimized for that. And so the dedicated servers got to take a lot of advantage of that as well. So this is what our C3 instance looks like. So just a base instance, we start it up, and we have a process on here that we call the process manager, the launcher. And so his job, given whatever instance it is, whether it's a C3, large, extra large, whatever size it is, we know how many processes of our game we can run on there. And so his job is, based on that type, to launch those. And so he'll start one, then he'll start the rest of them, and he'll make sure and maintain those. And so if anything happens to these guys, if they need to be cycled or something happens to them, he will always maintain that number of processes on that machine. So now we can take that, and so given that, we now have a machine that can have an IP address, a couple of ports on it. We'll back up here real quick. So each one of those green boxes is a process. It might have a different port, or it will have a different port. So as long as we know the C3 IP address to this one instance, we can give that to any of our clients, and then they can talk to any one of these 4 processes knowing the right port. They can connect to it, and so now we have a server running in Amazon. There's a couple of them on there, and then the clients can connect to it. So after that, we want to create a process that takes those servers that we're running and gives them to clients so they know where to go. Because right now, you would have to manually hand them an IP address and port. So our process actually starts even further back than that, is actually getting players together. The first thing we do is our matchmaking, and it's kind of our lobby-based system. So here we have a host and a client, and let's say they're in a party together or something like that. And I'm the host, and I decide that me and my buddy, we're gonna go find a game. So the first thing we do is we talk to matchmaking. And we're using first-party matchmaking. We're using Xbox Live, PSN, Steam. They are the matchmaking platform that we're talking to. So at this point, we're not even talking to any of our Amazon infrastructure. We're just getting players together in a game. So that lobby, as I was saying, is peer-to-peer. So it's not talking to anything else. They're just talking to each other. They're maintaining this peer-to-peer session within themselves. And this is actually a really important part for our early launch was this peer-to-peer network is actually a complete fallback for us, that at any moment, that host machine could be a server. Now, the experience is not as good as we'd like. It's definitely not as good as a dedicated server, but it could be, in the worst case, something that can run the game. And so we could use it as a fallback. It's also possible that if we decided to, for example, some game modes, we didn't want to have dedicated servers for that game modes, we could say, just run peer-to-peer. And so anybody playing that, say custom games or something like that, they could play in peer-to-peer. So this lobby is a client-host architecture, and it's always maintained. Even when you're playing on a dedicated server, the players all have a client-host kind of peer-to-peer connection going on, and we pass VoIP through that. It's also just a messaging interface. It's what happens when the game ends, you disconnect from the dedicated server. They're still in this configuration, talking to each other, get ready for the next map, whatever they're going to do. So now we've found 3 other people. So we've got a full game. We've got 5 guys. So they're all talking to each other in this peer-to-peer configuration. And now we can bring in our Amazon infrastructure. So here we've got a region, and we've got our external load balancer. And it's the host of this lobby. It's his job to make the request to Amazon or our infrastructure in Amazon. And so he says, hey, I need a game server for this game that we're playing. So now we can flip around and take a look at the other side here, which is, so when he's connected to that external load balancer, he's made a request, and now he's talking to our application servers. So over here, we've got the same game servers I was talking about before, and they've got those server instances on them. And so now they need to talk to the application servers as well. So we have an internal load balancer talking to our application servers. And so all of our game servers connect to that internal load balancer. And then they now have a database that's keeping track of that state. So you can imagine that, so these dedicated servers, they're constantly checking in. They're saying, hey, I'm idle. I'm ready to start a game. Here's where I'm at. This is my IP address and my port. And the application servers are tracking that. And then the servers keep checking in saying, am I still idle? Am I still idle? Just repeating that over. And we can have a whole bunch of these just scaled out sideways, all horizontal, and they're just all checking in, constantly saying, I'm idle. A request comes in, and now the application server changes the database and says, no, you're not idle. You're actually pending. And you have to start this map. It's going to have these players in it. They want this game configuration. This is the game you're going to launch. So the next time that server checks in, he finds out, OK, I need to start a game. So he knows that he needs to start a game, and with that, the polling interval is normally, say, 5 seconds when they're idle. So they're constantly hitting it over and over and over again. Now they're going to start a game, and that polling interval decreases. So now that they're running in a game, they're probably saying maybe 20 seconds. They'll check in, just constantly saying, hey, I'm running a game. This is my current state. What's interesting about that is when you have a lot of servers idle, so we kind of start all the servers up, we have a lot of space available, our load on our application servers is higher than when the player load is coming in, because when the servers are idle, they're hitting that system harder. And so as the player count increases, our server load decreases on our applications. Kind of an upside-down graph there. The other interesting piece is that because everything's constantly checking in, the database isn't actually required for persistence. It's only there because we needed a transactional data store. So if for any reason we blew that database away, it had an error or whatever, we just wiped it and we just put a new one in, within 20 seconds it would be fully repopulated and the system is completely operational again. So we've, that request went through, he got a server, the server came back, and now that IP port server configuration is being sent back to the host. He then sends that to the other clients, and all of the other clients now know, OK, over UDP, I connect to this IP address and port, and now we can run a game. So at this point, this is actually a shippable solution. You can have one region, servers running, players can find them, they can get a server, they can connect to a server, and they can play a game. So it's the full view into what you would need to run an online game. Now, we'll move forward to taking that even further, and we'll talk about the automation side of things. So obviously, one of the biggest reasons you want to automate is people suck. You can make as many checklists as you want. It's much procedure. They will always make mistakes. Computers are a lot better at following directions. So anything done manually is a liability. So for us, we built a server automation system. And most of that is our monitoring and operation system put together into one big application. It gave us a really nice area to set up authentication, authorization, and accounting. And that lets us make sure that we don't need to give everybody access to AWS if they want to view into our system. We can give them as much view as we want. We can give them as much control as we want. And we are able to run that internally and decide exactly what's going on. And so we also have any action that you can perform on the system through this is all predefined. And it may be very complex actions, something like, I want to start up a whole new region from scratch. You press one button, and it happens. You don't need to worry about following through on anything. It's just press it, forget, it'll happen. And then if anything goes wrong, we're tracking every step of the way, so we'll be able to research and figure out why and debug what happened there. So this is what our automation system looks like. We have an external load balancer, and then we have the web application, and then behind it is our user database. And in there is where we're defining who has access to this system, what level of access they have, and then deciding what actions can be taken. And then on this web database is also this UI where you can see, like, OK, I want to start an action, I want to do some tasks, things like that. So beyond that, we also have these services behind our system that we're using to maintain. And all of these are based on a lot of open source technologies that we didn't really want to have to modify to fit them into our system. But we wanted to give anybody access to it, but we wanted to control that access. So our solution was to put a custom proxy in front of it. And what happens is you make a request to our web app, and it says, OK, you want to look at our Grafana instance. We run Grafana, Graphite, Logstash. I'll go into those a little bit more later. So you'll say, hey, I want to go and get more information on this. I want to look at this screen. And it'll point you through our proxy. And the proxy will terminate your connection, verify all of your authentication, make sure you have access to this system, and then make the request on your behalf behind our application, and then return you the result. So that allows us to just throw authentication on top of any web application we want behind it. So now you can view everything, but then how do you make change? So that's where our API comes in. So you say you press a button in the web app, and it says start a server. That may be 15 tasks. Those 15 tasks go through the web API into the task database. So now we know, OK, these 15 things need to be done. So then we have another process, which is what we just call processor. It takes those 15 tasks and starts doing something with them. And this is the part that actually communicates with the AWS SDK. And so now you've got a system that you can view, you can modify. So then the important part here was that we have this API, and we also, I'll tell you about the auto-scaling system in a little bit, but that also communicates through this same API. And what's really good about that is the auto-scaling system is using the exact same system that we use to launch, scale down, or affect change to the entire system. It's using the exact same API. So along with the automation there, we also automate our build distribution. Every build is uploaded into Amazon S3. Whether we're going to use it or not, they all just go up there. It makes things a lot easier. So there's a story here about this 20 gigabyte per file limit in CloudFront. We had a beta. And so even if it looks like you might be able to use more than 20 gigabytes in CloudFront in small-scale testing, you can't when you scale up. They'll stop you real quick. And so the way that we distributed our server binary was through CloudFront. We just put them up in S3, and then we would let this CloudFront distribute it worldwide, and then our servers would just pull them straight out of CloudFront. What ended up happening is they started missing 100%, and so we were just routing all of our S3 calls straight through CloudFront servers to S3, and they just throttled the hell out of us. So that definitely gave us terrible bandwidth. So the solution real quick was to just hit S3 directly, but we needed something better. Went back to the drawing board, and we decided to just use baked AMIs. Definitely a much better solution. So what we do is our development servers will start up, and they can just run the game as normal. And then once a build is kind of approved and we know we want to go wide with it, we will bake it. And then once it's baked, it's distributed to all of the regions around the world, and then we can deploy it straight as a AMI. So this is what that process looks like. The build is uploaded into S3. The development boxes can just pull it straight out of S3, and they extract it to their ephemeral drives, and then that's now ready to go. Now we decide, OK, that server was fun. Everything was good. We can ship this thing. So now we're going to bake an AMI. So the first thing we do is we put the build on the EBS volume so that we can make an AMI out of it. So now we've created the AMI. And then now when this server launches, if we just boot that AMI, it'll just pull that build straight off the EBS, extract it there instead. And we no longer have any distribution problems. The AMI system is definitely a lot more bandwidth heavy. So in the automation, we have a lot of dependencies. Automation is really easy if you don't have dependencies, if you can just say, start a server, and there it is, right? And if you didn't have to find anything else, it didn't need to talk to anything else, you can just start a server, and away it goes. It's not that easy. We have MySQL servers we need to worry about. We have load balancers we need to worry about. We have salt configuration. We also have many other services that I haven't talked about yet. And every instance, we want it to be able to launch up, know where it is, and just discover all of its dependencies and talk to them immediately. So a solution for that we found is to use the instance metadata system in Amazon. That gave us everything we need for auto-discovery. And it doesn't require any SDK. We don't need IAM rules, and very little complexity. So we needed a base container to kind of hold everything together, and that was something that we could discover in the instance metadata. We decided to use subnets for that. That was something that you can discover, and it's something that you can have multiple of anywhere. And so we decided that was the smallest unit that we would put together, that if we launch any server anywhere, looking at its subnet, looking at its AZ, and looking at its region, it should be able to discover its neighboring services that it requires. And so this is what this looks like. So we have a single subnet here, and we're back to that same diagram I was showing before. We have our application servers, we have our internal load balancer, and we have our game servers and the database. So the first thing that happens is the game servers and the application servers now use their instance metadata to build a DNS address. This is a Route 53 address that we put together, and it's just US West 1A and the subnet name, and then whatever service it is they're looking for. And so in this case, it's the ELB. And so now they can say, OK, given this, I'll just talk to this address. And it just happens to be there. They just built it out of their own metadata. The application servers do the same thing for their database. They know exactly where it is. We've just mapped it all directly to the DNS address. So this works really well. And then we can expand that into a whole region with multiple subnets. So now we'll just throw a region external load balancer on top of it. And now we're balancing between multiple subnets within a single region. Now, the external load balancer doesn't have any AZ or subnet attached to it. So any client can find this knowing that US West 1 is the region. I'll talk to this ELB, and that is our external interface. So now we can put these in different AZs, and we're just balancing between them. Another thing we can do with these is, let's say we were having trouble scaling our database. For whatever reason, some emergency happened. Our database isn't scaling as we need it to. OK, well, we need to scale fast because we're running out of time, we're running out of space. We need to get servers for people. So one thing we can do is double up the subnets within a single AZ. And we immediately split our load in half. And it has cost us nothing. But there's actually a problem. If you try and use two subnets in one AZ in Amazon, it actually won't let you attach them to an ELB. So we actually have to run two ELBs there. And so we just do a DNS round robin against those 2 ELBs. And our system automatically knows that, hey, we decided to throw 2 subnets into an AZ. I better spin up another ELB there to take care of that load and connect everything together. So after that, we also have instance configuration. We use SaltStack for that. And all of our servers will download that configuration at startup. That includes the baked AMIs. Even though they do have a lot of stuff baked into them, we still keep the configurations live. This is really cool because if we decide that we need to change any of our configuration, we can do it, and it's within minutes. We can reboot all of our machines, and they will have the new configuration. And we don't have to rebake AMIs, which does take a while. We also do a pretty involved tagging process. When we launch an instance, we tag what it is, what it's going to do, so that way we can search for them really easily, both in the Amazon dashboard and using the SDK. We can look for these instances. Along with, during their startup process, they will tag themselves with their state, so that we're kind of using Amazon's tagging as kind of a feedback mechanism to know the health of an instance. If an instance doesn't get all the way to state 5 or whatever it is to be a live instance, we know something's wrong with that. We can search for those both with the SDK or in the dashboard, find them, kill them, investigate them, do whatever we need to do. But we can also filter them out to make sure that they're not used anywhere. So we know that any instance that doesn't make it all the way to these states, they don't tag themselves at those states, they're not healthy. So I described what one region looks like. So let's go further into a worldwide state. One thing that's important about global regions, and this is kind of something that I noticed make your lives a lot easier. When you're going global, use a VPN network. We did a big VPN mesh. It made life really easy. And it was really nice to be able to just directly SSH straight into any instance from your workstation. And so part of this, what we did is we have a lot of production VPCs, and one in every region. And then we also have 2 what we call operations VPCs. And these are where we keep our monitoring systems. It's where we keep our automated systems. And we have one of those in US West, and we have one of those in EU West. And so those are VPN connected to all of the production regions. And then our office is VPN connected to all of the production regions. And so we can connect from either spot of those directly to everything else. It makes things a lot easier, and it really simplifies the security group management because we basically have an internal set and an external set of security groups, and everything is specific to whatever that purpose is, and we don't have a lot of overlap. We don't have to worry about whitelisting IP addresses in any certain directions or everything. We know everything's going to go through our VPNs. So also when you're going global, region discovery becomes a big deal. You need to know what region players go to. Because I did describe one region, but now when you have multiples of them, you have to make sure they find the right one. So for that, we created a UDP ping service. We have one in every region. It measures quality of service. So we're measuring latency, packet loss. But at the same time, it's also measuring build availability. So the client knows what build he's running. And he's asking every region, hey, is this build available? And they can respond and say yes or no. And so that allows us to also roll builds out around the world. And so clients will never connect to a region that doesn't have servers for what they're looking for. Now, this service actually ended up extremely efficient. We would put it on, I think we were running M3s or something, I don't remember the exact size, but they basically were essentially doing nothing because responding to pings is a really easy process. So we decided to take advantage of the fact that we didn't really have much running there. And we also put a relay. And that was because we have the peer-to-peer network that we're doing for our lobbies. So we bounce any of those strict NAT configurations. I don't know if you guys have ever had to deal with NAT to NAT communication. That's a whole bunch of bull. So we just bounce any of the ones that aren't connecting. We just always bounce them off of our relay servers. So here's what that looks like. We bring those here, and then so we've got the two availability zones, our 2 subnets. They're completely separated. We've got our external load balancer, and then we bring our ping servers in. Now, even though the ping servers, and you can see that they also have their own service DNS here, so we've got the region, the ping service, so that anybody can discover them. And we just have, that's just a multi-IP DNS result there that's just telling you however many there are. The clients will just randomly pick one. We know they're all valid for the entire region. So even though those ping servers are within a single subnet, or they're kind of in both subnets, they actually represent the entire region. And that's important because even though the result comes back and it might be representing the state of a current subnet, the client will then make his request to an external load balancer that's balancing across all of your subnets. And so they need to represent the entire region. And so instead of communicating internally in their own subnet, they're always communicating with the external load balancer to get the information of the entire region. So they might be bouncing around kind of randomly between subnets, but at least they're giving us a pretty accurate view. Now, what's important to note also is that the subnets are pretty well balanced because the load balancer balances traffic across them. And so when we do scale these up, even though we may have two, they're almost perfectly 50-50. They stay pretty close. So what's also nice about having this ping service is that we have region failover. When clients are discovering what region they're going to talk to, they keep track of all of the regions that they've talked to and what the latencies were, and they rank them. So if anything goes wrong, we always know what the second best region is. And we've had this happen in production, and it creates a very interesting effect. So here we have the green line is the total number of players playing. The yellow line is US East 1, and the blue line is US West 2. So we were just having a normal day here. Everything was scaling up just fine, and then something went really wrong in US East 1. We couldn't scale up anymore. So we flatlined. We could not handle any more players. So players recognized that, the clients recognized that the servers were no longer working, they were getting denied, so they immediately went to their second best region. And so the second best for US East is US West. The latency is actually not that bad between the two, especially in our game, because we did set it up for peer-to-peer play. We were pretty good with higher latencies. And so in response, US West 2 just started carrying the load. And it carried that player load up until it took us, as long as it took us, to solve the issue. Players had no idea what was going on. They were just moving to a whole different data center. The only way they would have known is if they had measured the latency themselves. So as everything was going, the US East stayed flatlined. US West 2 was going up, and then we fixed the issue. And then we didn't do anything else. We just fixed the scaling issue. And then automatically the system was able to scale up, and the whole system rebalanced. And everybody that was playing out of US West that shouldn't have been, they moved back to US East. And then everybody that in US East just was able to play as normal. And you can see that the player total graph actually stays pretty linear, so you can kind of tell that that didn't really affect the player counts. So now we can talk about the auto scaling. It is a bit of a difficult problem. We couldn't use Amazon's AWS auto scaling. They were based off some metrics that we didn't want to use for our scaling. So what we ended up using was the ratio of servers in use to the total number of servers that we're running. And we do that on an individual subnet basis. And that's because we use subnets as our smallest container. We don't want anything outside of that to be part of any of the picture. So that makes everything completely independent. So if anything happens to a subnet, doesn't matter, we'll burn it, and we'll just launch another one, or we can just balance across the other ones. And so we use the same metrics that the application servers are using to know if a server is available. And that makes sure that if for whatever reason the scaling doesn't work properly, we can keep scaling or take action of some kind. But it won't just say like, oh, I've scaled up 5 servers. That must mean there's 5 servers available. We're actually using the exact same data the players are using to discover their servers. So one of the benefits we have with our game, and it's something we took a lot of advantage of, is that our rounds are generally about 12 minutes. At most, we actually cut them off. There's a timer that will force you to fight at 45 minutes. So we have the fact that no game can last longer than 45 minutes, and so we can use that to our advantage when we need to scale down something. We know that we don't need to migrate players. We just need to wait, and then eventually that game will be over. Other people might have some problems with that if you're running an MMO or something like that, where people can just stay in an instance for hours or days on time. So that's a slightly different problem. So we did have that advantage where we didn't need to worry about any kind of fragmentation. So normally, when you're talking about auto-scaling, you might be getting ready for some complex math. And actually, ours is not. It's actually very easy. So what we decided on was if we're over 80% utilization, we scale up 10%. If we're under 60% utilization, we scale down 10%. We sample very often, so that way we're keeping track of a lot of data, and we'll kind of average it out across the sample periods. But we make sure that our action period is no shorter than our scale-up time. So that way, if we ask for a server to start, we won't try and run another action until we know that those servers should have started by now. And that makes sure that we don't double scale up. We also track scale downs. We don't worry as much about scale downs. We would rather err on the side of having too many servers running if something goes wrong than not having enough servers. And so we do track them, but then we kind of let them scale down gracefully. So this is what that looks like. The yellow line is the total number of servers that are in-game at that moment. The blue line is the optimal 20%. So that way we have that 20% headroom. That green line is what our simple little algorithm gave us. And I would say it's not too bad. It's definitely not exact, but it's pretty close. We do have those flat lines there at the bottom. We do maintain a minimum. And that was just to keep the minimums at something reasonable. They start to scale down pretty low, and then things get a little wild. So we made sure that they don't scale too low overnight. And so we'll zoom in here on this middle one so you can kind of get a better view of what it looks like right up against the graphs there. So this is just a single scale up, and then the event starts to scale down. Now there's one thing I didn't talk about. With that simple scale up 10 after 80, scale down 10 after 60, one thing that we didn't take account of is that 10% there on the bottom left of the current player count is a lot different than 10% at the top of this peak. But if you look at that green line, that player count is pretty linear. So that scale up that we needed there at the beginning is pretty similar to the scale ups we needed to continue growing. So the way that we took advantage of that, or solved this problem, is we tracked the highest peak over the last week. And we say, OK, so what was the highest peak? And now anytime we need to scale up, we either take 10% of that highest peak, or we take 10% of the current. And that allows us to kind of keep everything in line, and that's what gave us the graph that we were looking at there. So now the visibility into this system. We track everything. I think it's, when we were doing our full testing, I think it was 2.5 million metrics per minute that we were tracking. We use Graphite for that data collection, Grafana for visualization, because it looks way cooler than Graphite. Everybody likes it looking cooler. So we're tracking. So we have statsd that's running on the machine, or collectd, and we're running that through statsd, and then we're also running all of our stuff through statsd. So everything gets together, and it's all merged into our Graphite system. And then we bring all of that into one giant monolithic I2 instance. And then, so an important part of trying to scale out Graphite is you need to define really good aggregation periods. If you try and say, I want to keep 1 minute granularity for 2.5 million metrics, you're going to run out of space really damn quick. So you want to kind of pick out the things that you want to keep for a long term, and then you pick out the things that you don't need for a very long while, and then you kind of adjust those aggregation periods. So when we were scaling out Graphite, one of the things that Graphite actually is pretty cool for is that it has this kind of caching mechanism where it'll say, like, oh, as the load increases, we can kind of cache in memory, and then we'll dump to disk to keep the I/O load low. We actually didn't like that because our worldwide loads didn't follow a perfect kind of up and down, and there was a lot of variability there, and it was kind of hard to predict. So we just went with shut that off. Every time a metric comes in, just write the whole thing to the disk. And we were able to do that because we were using the ephemeral drives on the I2 instances, which were huge. It gave us a lot of I/O ops, and then we just did another RAID 0 configuration on those. So the other thing with scaling out Graphite is it is a single-threaded process. So the only way to scale it is to run multiple processes. And that actually gets a bit complicated. So we have our I2 instance here. And the first thing we have is HA proxy. We're running, it's a TCP connection that we're balancing across here. So we're using HA proxy for that. Does some other things, but that's kind of what we're using it for. And there we have our Graphite relays. And so we're balancing our connections across these 4 relays. And then based on what metrics are coming in, we can decide if we want to aggregate it or if we're just going to pass it forward. And so we have to pass it forward because relays can only do one thing at a time. They can either decide to do rule-based routing, or these relays down here at the bottom, they can do consistent hashing and figure out which one of these caches they have to go to. And so we're running 4 of everything. All of these metrics are moving around in this system, and then all of that gets written to those stripe 0, RAID 0 ephemeral drives. So a lot of I/O going on there. Oh, and one thing I actually didn't mention from the earlier slide was that we're using Linux LVM snapshots so that we can do really quick backups without taking the server down. Gets us a complete total snapshot of the entire hard drive at any moment, and then we just back those up into S3, so we've got a snapshot every day. So then this is the data coming into the instance, and then obviously you need to be able to get the data out of that instance so you can look at it. So we have the Graphite web app is running here, and it's just talking directly to that data. Now, I don't know if you guys have ever had to create dashboards for executives. You'll tell them running a query is really expensive. Don't do it a lot. And they'll listen to you for the first 5 minutes. And you'll come back, and they're just sitting there clicking that button as fast as they can. They're like, no, it updates faster. And it's like, no, you're just taking the server down. So for that, we put varnish in front of it so they can click it as much as they want, and they get the same data back. But it makes it feel good, right? So then we take this same process. So that was one instance that we're running in one of those ops VPCs that I was talking about. So now we need to get all this data from the multiple regions into that instance. So we have here, let's say this is just, I don't know, US East 1. And he's got the 4 AZs here. A bunch of instances are all running. And now we have a separate instance here that is our relay instance. And in it, we're also running HA proxy. And it's also running 4 relays. Now, the reason for this is that if we were to just run any one of these straight to the HA proxy, we would be running a lot of data. Oh, actually, so there's one more step. There we go. So the relays are going directly to the relays in the HA proxy. And the reason for that is if we were to run the relays through the HA proxy there on that single instance, you would get the equivalent of all of US East is running down one path in that giant instance, which you don't want. You want to balance all of the instances across all of them. So that's why we have a second HA proxy in the region itself. Now, when the requests come in, they go to this region relay. And the reason we have this here is because we're actually running 2 of these things. We have one in our ops region in US West and one in our ops region in EU West. And it's the exact same data, constantly written to both of them all at the same time. So if anything happens anywhere, we can always go and look at either one at any moment. It gives us a perfect failover, hot spare of the entire system. And it also is a good sanity check. If we think something's going wrong in the monitoring system, we can look at the other one and go, oh, no, he's actually communicating properly. It's actually ways that we've seen issues in our VPN has been caused, and so we've been able to see it just by looking at the 2. Really, really good for debugging. So we also have Logstash, and we're logging essentially as much as we can. Logstash is actually fairly straightforward to scale. It's based on Elasticsearch. One of the big things that we notice is make sure you filter unnecessary data as early as possible. We have a lot of debugging data in our logs, and trying to scale out servers to handle a whole bunch of debugging data is just a lot of wasted time. So we make sure we filter that early. We only push stuff that we really kind of consider important for when we're trying to search for problems. And then once we can identify what instance it is, we can go and grab those logs, because we don't delete them. They stay on the instances. And we're using Logstash for both our application logs and all of our system logs. So we also have a crash collection system. And then for this, when a crash happens, we've piped into Linux's crash handling segfault system so that when it happens, we can take that crash, we upload it to S3, we also immediately launch GDB, and we take the call stack straight out of the crash. Then we take that call stack, we upload it to our own system, and we start aggregating those call stacks together. And we can say, OK, now we can go to this application, and we can see how many times this call stack has shown up, and we can rank them. And so we can say, OK, so this crash is happening a lot. We should focus our attention on that first and work backward from there. And then we can always link to the raw crash dumps in S3 if we want to get, and those crash dumps have the entire process memory space. And so if we want to debug further, see what any of the variables are, whatever the state of that process was, we can use that data for that. So that basically covers the high level of everything that we're running. So I'll kind of recap that real quick. So we have game servers in AWS, and it works. That's kind of useful. We automate everything. As much as we can, we try and automate it. We use subnets, metadata, and Route 53 for our auto configuration. We have region failover through our ping service. We auto scale at 10% over under 8060, and it's a pretty good system. It actually does work. And then we have a global scale of monitoring and operations. So there's 2. I don't know if you guys have ever had to be like the guy that's on call at 2 o'clock in the morning. That's always not a great experience. We've actually had a pretty good benefit. We've only had 2 real big issues happen. One of them I showed you was where we couldn't scale up in that US East, and that was one that we had to solve. And that actually wasn't one that anybody would have gotten woken up for, because the system kind of auto-heals itself. You could see that it would have stayed running that way as long as we needed it to until someone could come in and fix it. The other one was, my bad, I didn't set up the correct, our HTTPS certificate expired, and I didn't properly distribute that. So, and I get to be the one to take the blame for that one. So the only other outage we had was that. And then there was the one other major outage that actually caused dedicated servers to be exhausted was something that we didn't have automated, that we do now, is we deployed the client version of a patch before the servers have been deployed. And so the clients had something that didn't exist on our servers. And they all fell back to that peer-to-peer. So the players really didn't know that everything went wrong, but they were playing completely out of peer-to-peer. So we are hiring. This is what we were working on last year. We are working on bigger, better things now. You should come check it out. We'd be really interested to talk to you guys. So check out TurtleRockStudios.com. We have a career page there. And that's everything I've got for you.